questions. So I'd like to talk a little about techniques that can be utilized in HPTLC that are a little bit outside the box here because they're not as frequently embraced as they should be, and they offer tremendous power to the user of planar chromatography. First of all, just as a refresher, when we look at TLC versus HPTLC, there's some big changes there. So folks that are still using 20 by 20 traditional TLC plates, migration to high performance thin layer will save you not only on solvents, time, and money, but will give you enhanced performance in your separation, because the technique involves using plates with a very narrow particle size distribution, a very thin layer, which allows for more rapid development, higher resolution, and very important reproducibility, very good reproducibility with modern techniques. You can use this technology with the computer systems available today to do comparative analysis of historical samples against current materials, or to compare different plates run on different days or by different techniques. Using the compare feature allows you to compare a variety of records. The benefit of this is you can actually create digital reference standards in your laboratory. It is a multidimensional technique because in addition to the very feature-rich derivatization techniques you have for visualizing the samples, compounds, you can take advantage of densitometry to collect spectral data in the UV vis. You can also desorb bands directly into a mass spectrometer or collect them for offline analysis by NMR or FTIR. I'll show you some examples of that. This method is also quantitative, so you could perform a simultaneous identity requirement test and an assay test at the same time. So a lot of people often ask me, why do I promote HPTLC? Why am I such a big fan when we have modern HPLCs, and a lab like ours here at Flora Research, we have a number of LCs and LC-MS systems. And that's because it's one of the only parallel chromatography techniques available. You have multiple detections that can be performed on the same run versus being limited to whatever your detector is on LC. And because you're not reusing the plate, and this is really important, you can do experiments that may not work out, and you may be out of plate, but you're not out a $1,000 HPLC column. And so you have a lot more flexibility to experiment. Visualization techniques work so well with our human pattern recognition. We have this incredible ability to recognize patterns, and the colors and visualization techniques involved in planar chromatography, which are often very beautiful visualization techniques just from their appearance, can be immediately recognized by a trained analyst. Where looking at chromatographic overlays of peaks can be a lot less intuitive. While HPLC allows you to set up 100 or more samples to run unattended, TLC, you're going to be limited to a 15 sample load for a given plate. But with the newer technology, and this is important, which we'll learn about in a future event, you can actually run a stack of plates completely unattended with new technology that's becoming available from vendors. While it's a lower resolution technique than HPLC, it is a very good technique for a number of things. HPTLC in the United States is the gold standard for botanical identity. This is something that has become established and well recognized by a regulatory agency here, and companies working under 21 CFR Part 111 turn to planar chromatography as one of the main methods for performing the identity of botanicals. Compared to microscopy, it's a lot more deployable to newer scientists, where microscopy requires a lot of specialized training in histology with guidance from a senior person or training. A chromatographer can jump into this technique readily. The nice thing about it is you can plate confounding species right along with your authentic species, so that you can look at the patterns of both the species used to adulterate or get mixed up and the authentic one. And these techniques are now monographed in the United States Pharmacopoeia, which Wilmer will help us learn more about in a little bit. The nice thing about this too is this is all electronic now, it's all computerized, and will capture your data and archive it for posterity, which is an important fact that's required these days. For those of us that are older, we remember sketching the TLC plate or walking around the lab with Polaroids under our armpits or in our lab coat pockets. This technique now is a world apart from that. So I want to share some of my hacks that make TLC a much more powerful technique. And when I say TLC, I mean HPTLC. We started HPTLC in our lab in the 90s, and I don't think we've ever run TLC since then. One thing to keep in mind is reference methods may only report one or two visualization techniques. So when you go to a monograph, a journal, an SOP from another lab, they may be only looking at one visualization technique, but sometimes you can obtain additional visualization techniques which provide more information. We're going to look at that some more. When these plates are developed, remember, you can acquire additional data off that plate at no real cost. It's a few minutes of extra time, but one thing I see often is people will only look at the long wave post-derivatized, but not gather long wave and short wave pre-derivatized or short wave post-derivatized. We collect all images and then we put all plates through the scanning densitometer and collect in the low UV range. And this is a very valuable and informative set of data for ferreting out difficult to interpret samples and get to the answers. The compare feature is a great tool if you have it in your software for comparing historical samples. And often it can help because you can bring up multiple lots of material to compare side by side, even if they were run at different times, different places. This technique now allows for that comparison. And you can collect MS data as well. I want to give this example of Equisetum adulteration. On the left, we see that there is a greenish band at about 0.15 in this test sample on the first two samples lanes. The other two sample lanes are the authentic reference material. This would be indicative of a Palestra adulteration. But when you scan this at 350 nanometers, you can easily see a large peak that shows up, which is indicative of this adulteration. And you can see that data is very sharp and unequivocal. And in fact, there's methods for running EP reference in the HPTLC Association monographs where you can compare this peak intensity to the USP or the EP limit to determine if the material meets the pharmacopoeial requirements. This is a very interesting one here looking at Boraginaceae plants containing Alkannin and Shigonin. If you look at the white plate, then Viz on the far left, you can see that lanes 5 and 6 are indistinguishable. You see the two major phytochemical markers there, but these two species are not differentiated at all. When we took the extra step that wasn't in the paper of derivatizing and looking at long wave, we can then see two distinct blue fluorescing bands, which then under 210 nanometers scan prior to derivatization in the developed, we can see these two bands showing up as small peaks after the Alkannin band. So you can see from this that you can utilize densitometry, additional derivatization techniques like this UV long wave to enhance your understanding of the materials. If we would have stopped at the Viz in the procedure that we were studying under investigation, we would have said this method can't distinguish these things. But with a little extra derivatization, or if you don't want to derivatize, scanning at 210, we could quickly differentiate these materials. And that is a consistent feature. Let's look at turmeric here. The 4 lanes on the left there are turmeric sample plated at different levels, 2 different pulls. And you can see a blue band that's not characteristically found in turmeric. If you look at lanes 8 there, you'll see that blue band's not in the reference material. Now, we suspected this blue band is piperine because piperine is often incorporated into turmeric. The problem is that the ingredient specification of the manufacturer called for turmeric without piperine, and the vendor C of A said that this was 100% turmeric and there was no additives to the product at all. We plated black pepper on lanes 11 and 12 and piperine, marker for black pepper, on lanes 13 and 14. So we're pretty strong on that, seeing that same band at the same RF with the same colors. But then we sat on that band with our densitometer and collected spectral data in the UV range. So the noisy diffuse band at the top of that spectral data is the turmeric without piperine in lane 8, the same RF. And then you can see the overlays of the piperine standard from lane 14 and the turmeric band, lane 4. You can see that they match quite well. And indeed, this is definitely got piperine in it. Later, it was determined that it was incorporated into the product and was not properly labeled. Now, that might not seem like a big deal, but it's a big deal under 21 CFR Part 111 because the ingredient doesn't meet your specs, and therefore your product would be adulterated or misbranded. When we look at Guayusa and Monte, here's another example of going a little extra. Method we were replicating is using natural products reagent. But as you can see, lanes 5 and 6 and 7 and 8 are indistinguishable by NPR. You really can't see any difference between these two ilex species. But when we follow that with a spray from the derivatizer of sulfuric, we develop these nice red bands in the second sample, which distinguishes it quite nicely from the Guayusa. This is an example of taking an extra step in derivatization, doing a little experimentation. Sulfuric is a great universal reagent. It's really helpful in situations like this, and it can be oversprayed onto some of the other reagents like NPR, and you can obtain valuable information. So let's talk about qualitative and quantitative HPTLC. A lot of people don't really appreciate the power of quantitative HPTLC because they haven't had a lot of experience with it. But they're familiar with using planar techniques for identity, but it is very suitable for assay purposes. And you can actually combine these into a single method to do simultaneous analysis of multiple samples for identity and assay, which would greatly reduce cost for QC. Here's an example of lactose pellets where we did assays on lactose and sucrose. We applied our calibration standards through lanes 1 through 5, lanes 7 through 9 with a sample, 10 through 12 are spike samples, and then we have a suitability standard. Right away, this is a nice ID technique because the two compounds have different colors, and that makes them readily distinguishable with their different RFs and different colors. This is a densitomogram of that plate stacked at 550 nanometers. And you can see the two compounds nicely resolved and are integratable. This is the calibration curve that we did for lactose, and there's a similar one for sucrose. And you can see the green points represent the calibration standards. The blue points represent where all the samples fall. You can see the samples and the spikes there fall right between bracketed points, which is nice. We have a good linearity on the regression as well. So the result of this is we were able to confirm identity, and we were able to confirm the values of the lactose and sucrose in the product. This is a great technique because we've met identity, we've met assay requirements, we've done everything in one run: calibration, suitability, replicates, spikes, ID, and assay. That's a really fast technique. And if you start thinking about the number of types of assays you do in the lab by HPLC, you could greatly accelerate your throughput. I want to mention a little bit about HPTLC-Mass spectrometry. In our lab, we have a setup where we have a TLC-MS interface connected to an Agilent 6540 Q-top. This is an accurate mass spectrometer, and we use the interface 2 for this connection. This is a great technique for interrogating samples further, and you can see here some turmeric samples where we're desorbing a suspicious band we saw in long wave, which would be our piperine. This was a confirmation of that piperine in the turmeric. You can see the integrated chromatogram from the desorption. This mass spec is from the library hit for piperine, and you're seeing the isotope pattern for the compound, and you see the isotope spacing, isotope abundance, and ratios are all very tight, with a 99.68% match on the ID, and that is pretty good for coming right off a TLC plate. Another very interesting thing that you can do with this is interrogate other unknown bands. And an example in turmeric is the concern of Nimesulide. Nimesulide is an NSAID used for arthritis, and there have been reports of turmeric or curcumin products sold for pain management containing Nimesulide. And we utilize tandem mass spectrometry in this technique. And here we have desorbed this suspect band, and we've collected MS data, accurate mass, showing the hit for Nimesulide. This technique can be used for synthetic cannabinoids and cannabis products. It can be used for pharmaceutical adulteration and virility products, blood sugar support, and a variety of techniques. It's a great technique for the unknown compounds. There have been a number of times where people are stuck on a determination of authenticity with a botanical because a band shows up they haven't seen before, and they're not sure if this is variation within the species or regional harvest or weather conditions, what have you, or is this representing confounding species adulteration? With desorption into the mass spec, you could rapidly interrogate the band and get more data, which we love to be able to do. Again, if you don't want to desorb into mass spec, you could desorb into a vial and then take that sample and transfer it for NMR or for FTIR or for further chemical test or a secondary planar chromatography method or HPLC, whatever you'd like to do. It's a very fast technique and very easy to do. So modern HPTLC is a multidimensional tool for the complex sample analysis that we face today in our laboratory. And when you expand your routine methods beyond just one or two visualization techniques, you have a data multiplier, which really provides sound data support for your findings. With the piperine example, you collect spectral data on the UV, you collect mass spec data. It becomes an inarguable finding at a certain point, and that can be very important if you're one of the many vendors out there that are maybe needing to reject material and fighting a return authorization situation. Remember, don't be afraid to experiment with your plates. They're consumables. I know they're not free, but they're not $1,000 columns. So you can work with these, try different experiments. We have a TLC plate cutter. Sometimes we'll cut the plate up and we'll use different band applications and try different derivatizations just to see what we get. There's a lot you can do with this, and in the future, we'll discuss more of that. Also, remember, you have a quantitative tool here with the right technology, and that quantitative tool can be very powerful in the properly developed method for not only performing an identity test on a raw material, but an assay for potency. It can also be utilized for screening for certain contaminants. That's a powerful toolkit when you get all of that in one run. So I'd like to just thank Dr. Stacy Wise and Chance Jennings, two of our scientists here who worked very hard to gather this data together for my presentation. And I want to thank you for your attention.